Okay, so let's talk about the idea of Pearson's correlation coefficient. Pearson's correlation coefficient is a measurement of linear association. And this type of measurement applies only to data that has a measurement scale of interval or ratio. And very commonly we say at least interval. At least interval would be interval or ratio. Now the data is bivariate. And bivariate we mean that we take two measurements from the same, I'll say, element. As an example, we may take a person's height and weight. Both those measurements came from the same person. Now, notation-wise, Pearson's correlation coefficient, for the parameter, we use the Greek letter rho. It's pronounced R-H-O. And it's like a P with a slanted tail. The statistic we use is R, and it measures linear association. Now, there's some extremely important properties of correlation coefficient. First of all, the correlation coefficient is always on the interval -1 to 1. And those square brackets here, as a reminder from back in algebra, means that we include the endpoints. So the smallest a correlation coefficient can possibly be is -1, and the largest it can possibly be is a +1. It is mathematically impossible to be less than -1 or greater than a +1. It is mathematically impossible. Not only is it impossible, it actually has no meaning. Now, this is very, very important if you happen to be in my class. It is mathematically impossible to have a correlation less than -1 or bigger than +1. If you report a correlation less than -1 or greater than +1, you will lose more points than are possible on that problem. It's just like probabilities. Probabilities are on 0, 1. A negative probability has no meaning. A probability bigger than 1 has no meaning. My logic is if you could do something impossible, so can I. So this is extremely important. You cannot there's no technology out there that will give you a correlation coefficient less than -1 or bigger than 1. So if you end up with that value, then you've done something wrong. You didn't use the technology correctly. So let's take a look at a few examples. Now I'm drawing these all as if they're in quadrant 1, but that's not necessary. They could be in any quadrant. But just for sake of discussion, sometimes it's easier to think of it in quadrant 1. If I have a trend that looks like this, if I take a line through this, the line would fit it perfectly. This would mean that correlation, and I'm going to use sample correlations for here. Let's say this is sample data. This would be R equals 1. It's an absolute perfect alignment, although I kind of missed here a little bit. It's a perfect alignment, all the data. Likewise, if it was perfectly aligned with a negative trend, put a line through it, this would have a correlation of R equals -1. So a +1 is perfectly positively aligned, and -1 is perfectly negatively aligned. The angle here is not important other than it cannot be horizontal. If the data was perfectly aligned horizontal, that would mean that R equals 0. Because the key here is that as I increase values along the x-axis, I know exactly where I am on the y-axis. But if the data was lined up horizontally, as I increase values on the x-axis, it doesn't tell me anything. I'm always at the same y value. So it doesn't matter where I am on the x. So there's no connection. X tells me nothing about y. Likewise here, as I increase on the x values, the y values go down in a perfectly predictable pattern. We know exactly where we are, hence -1. So if correlation of 1 or negative 1 means we're positive or we're absolutely 100% perfectly aligned, then what could a correlation of negative 1.2 mean? What meaning could that possibly have? Could that be even more perfectly aligned? See, it doesn't make any sense. Likewise, what if we reported an R value of 1.3? What could that possibly mean? R of 1 means it's perfectly aligned. R of 1.3 means you don't know what you're talking about. This is not possible. It has no meaning, and it's mathematically not possible. So what happens is, as we start looking at scatter plots, as these points start to spread out a little bit more, the value of the correlation starts to shift anywhere between negative 1 and 1. So as an example, something perhaps like this, where there's a very obvious, very strong correlation. We can see there's no doubt that there's definitely a nice linear trend there. That may have a correlation of, I'm just guessing now, maybe like 0.8. If you look at our scatter plot and all you saw was a blob, earlier we said there's no trend there. Well, that would be R of 0. And then as this cloud starts to coalesce and begin to have a downward angle to it, this correlation may be a negative 0.8 or something like that. The actual value of the correlation is not important right now. We let technology figure that out. But I want you to get the idea of is as this cloud becomes tighter and tighter and tighter, it gets closer and closer to either a positive 1 or a negative 1. A 0 would be a blob that there's no trend to it. But that's not the only pattern that will give you a 0. Remember, Pearson's correlation measures linear association. So if I did a scatter plot, and let's just say we saw something like this. Say a perfect circle. Well, there's no doubt there's a very, very strong connection between x and y, but it's non-linear. So this would also give me r equals 0. Likewise, suppose I did something like this. That's what my data looked like when I did a scatter plot. Well, there's no doubt the trend is incredibly strong. This piece is probably a perfect negative 1. This is a perfect positive 1, a negative 1, positive 1. But the problem is Pearson's correlation looks very specifically for linear. It's going to see this as r equals 0. So if you actually saw something like this, you may have some type of temporal behavior. This could be a time element here on the x-axis that's causing this up and down sort of a pattern. In this course, we won't deal with trying to quantify the strength of this relationship. We're going to strictly limit ourselves to linear association, and in a little while I'm going to talk about monotonic association in another form of correlation to measure it. So let's take a quick look at an example here. This is an example we looked at in an earlier chapter, but all we do is a scatter plot. The idea here is that fishermen in Finger Lakes region have been, and this is Finger Lakes, New York, have been recording the dead fish they encounter while fishing in the region. The Department of Environmental Conservation monitored the pollution index for Finger Lakes region. The data table below shows the information for the past 8 years. Actually, it's between 1987 and 1993. This is somewhat older data. So this is the pollution index, and these are the deaths. And what you'd expect to see something that looks like this. You expect if this is the, actually I want pollution down here. This is the pollution index, and this is the deaths. We'd expect to see something like this. The initial logic would be as the pollution increases, so will the deaths. So we expect to see a positive linear trend. So we need to plot this data and take a look at it. So here we are in TC Stats. The year, that's just a label. We're not going to work with that. The pollution index, I'm going to go ahead and set that as being ratio. The deaths, I'm going to set as also being ratio. And then the idea here now is to go ahead and create a scatter plot. So I will go to Graphs, select Scatter Plot, and I want the pollution index to be the X variable and the deaths to be the Y variable. If you happen to get them in wrong order, all you got to do is tap on switch order and it'll change it for you. And I'm going to tell it to, I'm going to leave Pearson's correlation on. I'm going to turn off Spearman's because we haven't talked about it yet. I'm going to turn off the residuals. And we're going to ignore all this stuff regarding the hypothesis test right now. So my first thing here is simply to take a look at a scatter plot. So I'll tap graph. And sure enough, it's exactly what I'm seeing is some form of linear trend. It's pretty obvious this is linear. Now the question now becomes, how strong is this association? So if I tap on the results, because I told it to leave Pearson's correlation on, this is a bunch of stuff that relates to linear regression, which we'll come back to a little bit. But this is the value I'm looking for right here. Pearson's correlation is 0.9286. It's very, very, very strong. Now, I want to go back and thinking in terms that we would expect a linear trend. What we do is I set up a hypothesis statement. So the null hypothesis is rho. The correlation coefficient is 0, meaning no association. And the alternative hypothesis is that rho is greater than 0 because I'm expecting a positive association. And alpha probably 0.05 like we typically do. You can change that depending on the severity of a type 1 error. And now when we go back to TC stats, this hypothesis test would make sense. So if I go back to results, well actually I want to go back even farther. I want to go back and set it. So the hypothesis test, the null hypothesis for correlation, I'm going to set this to equal to 0. Technically it should be less than or equal to, but I've talked about this before. I just prefer my students make it equal, make life a little bit easier. The alternative hypothesis is greater than 0. And then when I hit graph, then tap on results, then obviously this p-value would make sense now. Here's your correlation coefficient and a p-value is 0.0004, meaning that it suggests there's very strong evidence that this positive linear trend that we're seeing is real and not simply a matter of chance. So based on the p-value of 0.0004, now it's very important that you make these rows with some type of tail so you don't confuse it and think it's a p, because it's not. All right, so the p-value is 0.0004, so the decision would be to reject the null hypothesis and state the conclusion that there is evidence, I'll say sufficient evidence, to suggest, I say, a positive association between pollution index and deaths. Obviously we're talking about fish here. So what we're seeing is that as deaths increases, so does the, as the pollution index increases, so does the number of deaths. Now, this is not the same as causation. We cannot make the causal leap. We cannot say that the pollution is actually causing the increase in deaths, although it certainly feels that way, and it's a logical thing to want to say. Just that mathematically and all the theory behind correlation, we cannot make that causal connection. There are many, many, many other possible contributing factors that could be causing the increase of death in the fish. This could be very likely a contributing factor, but to say that it is actual causal is not a good idea. So it's important to understand that correlation does not equal causation. We are measuring the strength of the association between two variables, not determining if one variable actually caused the other to happen.